Sorry for the delay. Hello, everyone. Thank you for attending this talk. I'm Xiao Li, a PhD student from UC Riverside. This work is done in collaboration with Farzin, Houshmand, and Professor Mohsen Lesani. Today, we're going to talk about resilient partitioning and replication. So let's imagine a billing service for a healthcare system. This system includes different organizations, including hospital, insurance company, and patients. And they can use a different cloud infrastructure to host their microservices to provide scalability and availability. And also, they host some of their data and computation on the private on-premise cloud. So for this system, that can include some Byzantine servers. That means those servers can perform arbitrary behaviors. And now we have a distributed system that spans different organizations to complete one service. And for this billing service, we have some security policies. The users of the patients may want its medical record to be confidential so that it can only be accessed by it cannot be accessed by the insurance company. And similarly, for integrity and availability, we have some requirements too. We want this service to have integrity and stays available even if there are failures for the servers and malicious attacks. So how can we support all these security policies? Some existing work, including Fabric, are using information flow control to support confidentiality and integrity. But however, they do not support availability. Other works, including KIMP, are using a Byzantine quorum replication, but those quorums need to be inputted by the user instead of generated. In the context of the related work, we support all the three mentioned security policies, and we are in the heterogeneous host setting. We are the first one that automatically partitioning the methods and objects, and we synthesize a resilient distributed system. We want the programmers to input a sequential program for service, and they can define their end-to-end policies for confidentiality, integrity, and availability as type annotations. The output should be a distributed system that guarantees all those properties in the face of Byzantine attacks. We propose a synthesizer HAMRAZ that automatically partitions and replicates the objects and methods. So the first question is, how can we capture the sequential program and then the security policy for this system? We propose a security type language and lattices of trustworthiness types. Let's start with an example. So here we have three parties. Principal A stores a value on register R1, principal B stores a value on register R2, and also we have a client P0 wants to access one of the value and access it only once. So here we define a one-time transfer method. This is a centralized definition without any distribution details. It first defines two field objects, R1 and R2. And next, it defines a register R to store whether the client has already read or not. So for this transfer, it will take in a Boolean parameter to indicating the client's choice. If the client has already read, this method will simply return 0. If not, it will store this register R to be true to indicating that the client is reading. And then it can return either R1 or R2's value based on the client's choice. So for principal A and principal B, they can have several servers. These servers can be Byzantine, which means they can perform arbitrary behaviors. Here, the small b is a attack scenario that includes Byzantine principal A1, A5, and B2. And this is another attack scenario. In this attack scenario, we have Byzantine principals A2, A6, and B3. And then we can capture those attack scenarios inside a resilient type capital B. This capital B is a set of attack scenarios that we want to be resilient against. And we can also use this concise notation to represent any set of 2A and 1B Byzantine principles. So for this one-time transfer, we define some security policies for it. For this R1, we only want the principal A and the client P0 access it. And similarly, for R2, we want the set B and P0 to access it. And we also define security policies for the return type of this method. For the return, it should be confidential and only the client can read it. And it should the return value should have integrity even if 2A and 1B principals are Byzantine, and stays available even if 1A and 1B principals are Byzantine. So as we saw in the example, we define the trustworthiness type as a triple, which includes confidentiality, integrity, and availability. Each of them is represented as a lattice. For confidentiality, it's a set of nodes that are trusted. For integrity and availability, they are sets of sets, which is the resiliency type we just defined. The next question is how can we partition a sequential program? We perform a program partitioning technique in 2 steps. So since we see in the security policy from user, the client P0 can access both R1 and R2. Then the question is, why don't we just host the home methods and all the objects on the client P0? Because in that sense, if the client is attacked and it's only one replica, we do not provide any integrity or availability for this home methods. So we split the programs into different partitions so that this R1 read and R2 read are replicated on different methods, M1 and M2, as shown in this partition. We perform this partitioning in 2 steps. The first step is the Cps transformation. So from the left-hand side to the middle, we factor the program so that all the object methods calls are explicit call expressions here, and they are at the top of the branches. And next, we perform a partitioning transformation. To allow maximum flexibility, we enforce that each partition calls at most one object method call. Now with the splitted methods, the next question is how can we infer the placement and the replication for those objects and the splitted methods? We use an information flow type inference system to achieve that goal. So imagine that we are placing a method M on this first replica. And when should we execute this method M? It shouldn't be the time when a Byzantine server asks us to do so, because in that case, we do not have any integrity for this parameter. So if we want to be resilient against 2 Byzantine principals, we need to receive the call request from at least 3 principals so that there is a correct one. And that can be any set of 3 principals. So from that, we get a set of quorums, which is a communication quorum system. And then the next question is, how much should we replicate this method M? If we just host it on one replica, which is this first replica, and that one can be a Byzantine. And if this method is calling a subsequent method, that call may not happen. So let's assume that the next method requires 3 call requests to execute. And we want to stay available even if 2 principals are Byzantine. Then we need to replicate this method at least 5 times, so there are 3 correct principals actually sending this call request for the following methods. From that, we get a set of hosts. We have those 2 components for a field object, and additionally, we have a storage quorum system. So with two Byzantine principals, if we write to and read from 3 principals, then the intersection can be Byzantine, and we do not have any integrity for that. So we need to write to and read from at least 5 principals so that the intersection contains at least 1 correct node. Any set of 5 principals will be a storage quorum system for this field object. So for a field object, we're going to have a set of host H, a storage quorum system QS that is to store this field object, and a communication quorum system QC to receive the call request from. Now let us see how can we change this partition method through the quorum systems. So here are our partition methods. Here this method M3 is calling M1. And we assume that M3 is hosted on B2 to B4, and M1 is hosted on A2 to A5. And we assume that A1 and B2 are Byzantine principals here. So here we see that the communication quorum system for M1 includes any set of 2 B nodes. Here we have 2 correct principals are hosting this M3. So they will send the call request to M1, and M1 will receive this 2 correct call requests and then execute. Then the next step is for this M1 to calling response to return the value to the user. Here the 3 correct principles is enough for the communication quorum system for response. So response will accepts those call requests, and then return. So previously, we are assuming that we've already got the replication and placement for all the objects and the methods. But how can we automatically infer them? From our previous step, we've already got the user's security policies as trustworthiness types, and we've already split the methods. Now we want to infer the types of each expression inside this sequential program so that we can get the proper placement and minimize the replication. We define an information flow type inference system for that. So we will get the constraints for the types, type variables, placements, and replications. And this type inference system will respect users' policies. Let's see one rule for an example. This rule, we are type checking that the information flow for a method called M is proper. So we will focus on the availability check. Here, this rule first retrieves the type of this method M, and we can see that the parameter type is tau1, and the availability component of this tau1 is A1, and it next retrieves the communication quorum as Q. Finally, we check that if the communication quorums are restricted to the current host H, then it provides more availability than required, which is A1. So this is the example we see before. For this response, its communication quorum includes any set of 3A or 2B nodes. And here we are replicating this M1 on 4 principles. And if we excluding the Byzantine ones as required, which is indicating as this A here, it's any set of 1A and 1B nodes, then we still get three principles will send this call request for the response. So that is enough for the response to execute. Now that we've already collected the constraints, the next step is to actually solve the constraints. In order to do that, we translate our constraints to the theory of linear arithmetic. So here we are going to see an example. How can we represent these quorum systems and resiliency types? This 2A and 1B principles is what we just saw. We can translate that to a tuple of integers. We translate that to a tuple of 2, 1, 0. And if we union them together, they can represent the quorum systems and resiliency types. So we will see one constraint based on this representation. In this constraint, we are checking that the communication quorum Q is more than the resiliency type B. That means any quorum inside this Q is not contained in any attack scenarios inside this B. So we translate that in this form in the right-hand side. We're checking that any tuple inside any tuple I inside Q, any tuple I prime inside B for at least one principal domain, we have that Qij is larger than the Bi prime j. So we formally prove that our type system guarantees non-interference and resiliency properties. First of all, we prove that while type methods are not interfered by changing the states of objects with higher confidentiality, lower integrity, and availability. Next, we prove that our type system is resilient to attacks of subtypes. So the final step is to instantiate and assemble the protocols and run it in a distributed system. We run our experiments with 6 small use cases on a cluster of nodes. In this table, we will show that HAMRAZ can synthesize resilient distributed system in an order of minutes, which is a reasonable time for static analysis. In this experiment, we are fixing the resiliency specification, and we increase the Byzantine faults up to their policy. And we show that the synthesis system can gracefully tolerate the Byzantine attacks, and and the whole system stays responsive. In the last experiments, we are fixing the attacks and increasing the resiliency specifications. We show that our synthesizer can scale and adjust replication proportionally to the strength of the policies. So in summary, we want a program able to input a sequential program and their security policies for this program. And we can output a distributed system that guarantees these policies in the face of Byzantine attacks. In order to achieve that, we define a security type language and type lattices, a partitioning transformation, a type inference system to guarantee the non-interference property, And lastly, constraint solving technique to infer the placement and replication. Thank you.
All right, great. Thanks for the wonderful work. If you have any question, please use the microphone.
First of all, thank you. This is really cool. I hadn't thought of using type systems to try to model availability. It's really neat that this is what happens when you do that. I'm curious whether or not you think this approach would be able to generalize to settings in which the compromised servers are adaptive. So there's sort of some adversary that can compromise one server and then decompromise it and later compromise another.
I'm not sure I get your question. So you are asking about the thread model that the server that are compromised one by one, or they can like cooperate to do some malicious attack?
Yeah, they can be dynamically compromised and then uncompromised, and you just have like some bound on the total number.
Okay. So for that, I think currently our system is assuming that if you are a Byzantine server, then you are compromised at the beginning of the execution. So if you want to really capture the Byzantine behavior of the system at runtime, I don't think there's a failure detector to do that. So you have to like set a bound for it.
Okay, cool. Thank you.
All right, we still have 2 minutes. Any other question? Maybe I will ask one. So yeah, this is a very interesting work. Can you share any information about any future work along this road?
Yes, so for this information flow control technique, it's kind of conservative for the real world system. So I think our next work will include some declassification or endorsement technique to make this system more flexible. And maybe we can extend to use that on the object-based languages like Java and C++. Yeah, that's our ultimate goal.
All right, great, wonderful. So let's thank the speaker again.